Hello everyone, welcome again to Integral Calculus, and for today's video, we would be discussing about the integration by trigonometric substitution. But disclaimer first guys, before watching this video, it is imperative for you to master first some pre-calculus subjects such as your trigonometry, and of course you must master first differential calculus before watching this video. And about trigonometry, you must know by heart these trigonometric identities listed here. So these are to be some of the trigonometric identities but are not limited to. But it is once again imperative for you to know them by heart. So one example of a trigonometric identity is that your sine theta is actually the inverse of your cosecant theta and vice versa. So with that, what I mean is that your cosecant theta is also equal to your inverse of your sine theta. So once again, just refer to this table right here. Okay, so going back to this slide right here. So in using your trigonometric substitution, it would basically have the same goal as when you are to use algebraic substitution, which is the simplification of a complicated integral equation. So that is what both of these share in common. But the major difference is that in trigonometric substitution, you are to follow certain rules before you can substitute. So unlike in algebraic substitution, you can just substitute any variable you want to any variable or any function that is included in the integral equation. So let's have an example for this trigonometric substitution. But first, let's talk about the rules that I was talking about earlier. So these are the rules that you would be taking into consideration. So for example, that in your integral equation, you would be seeing a term which is very similar to this. What you would be doing is that you would be substituting a sine theta to your value of u. And as for this one right here, if your equation does have this term right here, which is a squared plus u squared, what you would be doing is that you would be substituting a tangent theta to u. So let's have an example. So for pretend that your integral equation does have this certain term right here, which is, let's say, 81 minus x squared. So guys, this can be rewritten as 9 squared minus x squared. And as you can see here, this term right here is basically the same as this one right here. So from that, what we would be doing here is that we would be substituting x with this one right here, which is a sine theta. And our a right now is to be 9. So from that, this equation would now look like this. So 9 squared minus 9 sine theta squared. We can simplify this further with this equation. So 9 squared minus 9 squared sine squared theta. And factoring out 9 squared, so this is to become 9 squared times 1 minus sine squared theta. So this is to be your equation. But once again, speaking about our trigonometric identities, so if you are to look at this value right here, it is basically this one right here. So for your cosine squared theta, using your Pythagorean identities, that is to be equal to 1 minus sine squared theta. And if you would be looking at this part right here, so meaning that this is to be 9 squared times cosine squared theta. So using trigonometric identity. Okay, so to understand our lesson better, it is better for us to have an illustrative example. So in this illustrative example, we are to solve for the integral of dx divided by x squared times the square root of 4 minus x squared. And as you might have known already, we cannot solve for this one right here using our basic integral formulas like this one right here. So we cannot use our power formula, we cannot use this solution right here or this formula right here, and we cannot use any of this formula right here right away. So what we would be doing is that we would be making use of our trigonometric substitution for us to simplify this complicated integral equation right here. So there. Okay, so as you can see here, we have this term right here, which is 4 minus x squared. And as you can see, this is quite similar to this equation right here. So from that, I would be rewriting this term right here as 2 squared minus x squared. So from that, you can see that it is basically this one right here, where your value of your a is equal to 2 and the value for your u is equal to x, which is this one right here. So substituting u is equal to a sine theta. So from that, our u now should be equal to a sine theta. So there. So from that, this is to be its new equation. So this is to be 2 squared minus a sine theta, and our a is equal to 2 sine theta squared. So this is to be our new term for this part right here. So rewriting this equation right here, this is to be equal to the integral of dx. Oops, by the way, guys, your u is equal to your x, and your x is equal to a sine theta, which is 2 sine theta. So if we are to get the derivative of this part right here, so meaning our dx is now equal to, so what is to be the derivative of this one right here? That is to be 2 times cosine theta times d theta. So there. And using this equation right here, we can now substitute it to this term right here, which is dx. So from that, this is to be our new formula. So this is to be our new equation. So 2 cosine theta d theta. So that is for the numerator part. And as for the denominator part, so what is to be x squared? So your x once again is equal to 2 sine theta. So from that, 2 sine theta squared times the square root of 4 minus x squared. So what would be our x squared? That is to be 2 sine theta squared. So this right here is to be our new equation for this one right here using integration by trigonometric substitution. Okay, so simplifying this one right here, this can now be written as, so the square root of 2 cosine theta d theta divided by, so what is 2 sine theta squared? So this is to be 4 times sine squared theta. So this is to be this part right here. And as for this one right here inside the radical symbol, so this is to be the square root of 4 minus 4 sine squared theta. Simplifying this equation, this is to be equal to the integral of 2 cosine theta d theta divided by 4 sine squared theta times the square root of, so once again, factoring out 4, so 4 times 1 minus sine squared theta. And just like what I have said earlier, that this is to be an identity of cosine squared theta. Simplifying our equation right here, this can now be rewritten as 2 cosine theta d theta divided by, so 4 sine squared theta square root of 4 cosine squared theta. So cosine squared theta. So I would just be writing it here. So this is now to be equal to, so the integral of 2 cosine theta d theta divided by 4 sine squared theta times 2 cosine theta. Since the square root of 4 cosine squared theta is equal to 2 cosine theta. So from that, we can cancel these terms right here since they are similar, and we will now be having this equation instead. So this is now to be equal to the integral of d theta divided by 4 sine squared theta. And as you can see in this part right here, so your sine squared theta is actually equal to, so this can be rewritten as the integral of cosecant squared theta d theta divided by 4. Since using your trigonometric identities, 1 divided by sine squared theta is basically equal to cosecant squared theta. So now that we have simplified our equation, what we would be doing is that we would be getting the integral of this using the basic formulas we know. So the integral of cosecant squared theta is equal to negative cotangent u plus c. So from that, this can now be, the answer here would now be equal to, so 1/4, which is this 4 right here, times negative cotangent theta plus c. So there. Okay, so the answer for your transformed equation is to be equal to 1/4 times negative cotangent theta plus c. So what we would be doing next, similarly to what we have been doing in the integration by algebraic substitution, is that we would be substituting these values right here to divert it back to this case right here, which is in terms of x. Since we are to deal with trigonometric identities, what we would be doing right now is to get the relations of it using these equations right here. Okay, so what do I mean there? So as you can see, our x, once again, is equal to 2 sine theta. So that is according to this one right here. So x, once again, is equal to 2 sine theta. And cross-multiplying this, so sine theta is now equal to x over 2. So once again, what I did here was just to cross-multiply. So if you can remember your identities, and let's say this terms right here, which is SOHCAHTOA. So ka, toa. So in your sine, so from this right here, your sine is equal to, sine theta is equal to opposite over hypotenuse. So meaning, referring to this relation right here, it means that in a given right triangle, this is to be your opposite side, and this one right here is to be your hypotenuse. So if we are to draw a triangle right here, so this is to be your triangle. So let's say that this is to be your triangle, and let's say that this is to be your angle theta. So this is to be your angle theta. The hypotenuse is equal to 2. And the opposite side is equal to x. So what about for this side right here? So via Pythagorean theorem, so this is to be equal to the square root of your hypotenuse squared, so 2 squared, minus your opposite squared, which is x squared. So simplifying this further, this is now to be equal to 4 minus x squared. So this is to be for your value here. But your answer here is in terms of cotangent theta. For your cotangent theta, so your cotangent theta, using the identities that I have shown to you a while back, cotangent theta is actually the inverse of your tangent theta. And for your tangent theta, it is to be equal to, so tangent theta is equal to opposite over adjacent. So this is via this equation right here, which is tangent is equal to opposite over adjacent. So if your cotangent is to be the inverse of your tangent theta, it means that this is to be having this equation right here, which is adjacent over opposite. So for your value of your cotangent theta, which is, well, in this part right here, so I would just be copying this one at the bottom part. So as you can see in this part right here, we are to deal with cotangent theta. And for us to know the value of our cotangent theta, that is to be equal to adjacent divided by opposite. So using this triangle right here, if this is to be your angle, that is to be the adjacent, which is the square root of 4 minus x squared divided by opposite, and our opposite in this angle right here, the opposite of this angle right here is to be this x right here, so that this is to be equal to x. So substituting this value right here, since this is to be your cotangent theta, so here, so this is to be your cotangent theta, substituting known values, this is now to be equal to 1/4 times negative square root of 4 minus x squared divided by x plus c. So plus c. So simplifying this further, this would now be equal to, so this is to be equal to negative square root of 4 minus x squared divided by 4x plus c. So this is to be your final answer for the given integration problem.